The goal of this experiment is to determine how nozzle diameter affects the thrust produced by a water rocket. Our team will measure thrust using a calibrated load cell while launching a pressurized 2-liter water rocket with interchangeable nozzles. By testing several nozzle diameters and recording the resulting thrust, we aim to identify the relationship between nozzle size and rocket performance. We expect that nozzle diameter will significantly influence thrust production. Too large of a nozzle size will result in a rapid drop in internal pressure, thus reducing the duration and overall force of thrust. But a nozzle size too small will restrict flow and limit thrust. Because of this trade-off, we expect to observe an optimal nozzle diameter that produces a maximum thrust and efficiency. The course topics covered in this experiment include the following: sensor calibration, uncertainty analysis and propagation, and experimental design principles. The load cell must be properly calibrated to convert the load cell's voltage output into a measurable force. Measurement uncertainties from instruments such as the load cell, pressure gauges, and calibers will be quantified and propagated through the governing equations to determine the overall uncertainty. Variables such as water mass, bottle type, and pressure are controlled to ensure that the only independent variable affecting thrust is the nozzle diameter.
For our instrumentation project, we are measuring the thrust of bottle rockets, specifically the difference in thrust produced by differing diameters and nozzle size. And in order to do that and also minimize the error that we might face, we have built an apparatus that is able to withstand at least 490 newtons of force. And the bottle itself will be pumped up to 60 pounds per square inch. And essentially on top of the bottle there will be a load cell that is tiered at that point, and with the thrust it'll measure the force that the bottle moves up with once the bottle's released. And the only potential errors there that could be are specifically bias errors. Like I mentioned before, the load cell will be resting on top of the bottle, and so we'll have to account for that extra amount of force, mainly just from gravity. But there will be a resistance to keep the load cell from moving up once the rocket is released. And there might be some slight precision error, but in order to combat that, again, we have a track, basically a frame that the bottle sits in, to prevent too much movement from side to side.
2, 1.
Not bad. In our next launch, we'll be using another set of washers on the test frame to hold the load cell at a specific length above the testing setup. We'll also be using a pump with a better resolution. This one seemed to dance around its numbers. And from there, the last challenge will be installing an actual load cell, as right now we are just using a representative.
Our test rig has been pumped to 40 psi. We fill it with a liter of water. Now we will launch. There we go.
This is our thrust stand contraption. Some safety features on it. We've got holes in each of the 4 corners, and we're going to stake this down into the ground so it does not go up when our bottle is launched. So we've got a bottle with a nozzle. We're going to fill it up with a liter of water. It's going to be inserted, and this top piece with our load cell is going to be placed on top, and then will be bolted down with some wing nuts. We will then pressurize it to about 50 psi, then stand back from a safe distance using our cord to actuate our quick release, allowing for the bottle to launch. The load cell will then take measurements over a given time through its through the launch cycle sequence.